department in computer science at the University of Toronto, but he has cross appointments in the Department of Psychology and Statistics as well. And he's a faculty affiliate at the Bechter Institute for Artificial Intelligence. He was previously an assistant professor at the School of Computing at National University of Singapore. He did have research fellow positions at Harvard and Stanford after receiving his PhD in computational cognitive science from University of Berkeley, where he applied Bayesian statistics and machine learning to model how people learn and reason. He currently leads the Intelligent Adaptive Intervention Research Group at the University of Toronto with a research agenda guided by redesigning technology for people, with applications like education and health behavior change. They combine human-computer interaction and psychology to conduct randomized A/B comparisons in real-world settings, for example, online homework, text messaging, interventions, and apps, and apply statistics and machine learning methods like multi-arm banding algorithms to dynamically adapt randomized A/B comparisons to enhance and personalize the experience for future people, balancing practical impact with conducting scientific research. So the work he's going to present today, and I'm really excited to hear about it, aims to address this underappreciated complexity of using adaptive experimentation to both enable scientific and statistical discovery and help real-world users. So Joseph, a big pleasure, and over to you.
Great, thanks so much. So great to see everyone. Not that I can see people because they're all hidden behind the presentation, but please feel free to drop stuff into chat and ask questions or anything else like that. And this is actually joint work with Nina Deleu and Sofia Villar. So I'm not sure how much of it you all have seen before, but feel free to ask questions about it. And Nina and Sofia jump in and interrupt and like ask me to explain something again or add some context. When you present a presentation, you're not in the audience's head, so you all are a bit closer to them. And I mean, you all probably, see Sofia and Nina around all the time, and they're at your institution, so you take them for granted. But from our lab's perspective, being able to work with Sofia and Nina on these bandit problems is one of the most exciting things we do. We think of them as world experts in how to do statistical analysis of data from adaptive experiments. So it's been a pleasure doing all of this work together. So just to kind of kick off, this is a brand new talk. I threw a bunch of things together because I prefer to present something new than something old. So I welcome feedback on the problem, the ideas, the approaches, suggestions for literature, criticisms, concerns. I also want to mention, as I'm cross-appointed in statistical sciences, so the first PhD student I took is actually starting this year, Tong Li, and he's actually in this call, I think. If you all have other people want to apply, please let me know. And we have a lot of top undergraduates at the University of Toronto, so if you're interested in having them apply to work at Cambridge and biostats, let me know. I'll be happy to pass on information. And spam the chat with comments, questions, thoughts. Even if I don't see them right away, I can respond after. And I'll try my best to speak slower. I have a problem where I speak way too fast. I'm from Trinidad and Tobago in the Caribbean, and so it'll sound like I'm speaking 10 times faster than normal. But Trinidadians also speak much faster than average. So don't hesitate to interrupt me or just say speak slower. Great, so this is the Intelligent Adaptive Interventions group, and we actually have, this is who will be starting in September. It's a range of grad students from backgrounds from statistics like Tong, as well as computer science grad students who already want to be trained in statistics. And so that's why it's great to give talks with these kinds of groups. And I'm really keen on having computer science grad students be trained in statistics, as much as possible so that they can actually do the kind of research that crosses machine learning with statistical sciences. So to give you a bit of an overview, I'll start by actually just kind of explaining, what I mean by adaptive experimentation in terms of helping future participants, and how we see adaptive experiments as an engine for improving user interfaces for health behavior change and education. Then the first set of research is about how do we characterize some of the biases in adaptive data collection in a particular empirical context. How do we modify statistical tests using properties of the algorithm used to collect data? And then how we modify algorithms to improve the quality of the data collected so you can do better analysis. And then turning to some of the future work ongoing directions we have now. So when we say adaptive experimentation, what we're thinking of is when the property of assignment to arms or conditions in an experiment is changing while data collection is ongoing. So one example of a goal is how do we adapt a field experiment to give students better arms while it's running? So you might randomize students to arm or explanation A versus explanation B, And the reward or the outcome variable is whether students judge the explanation is helpful, get a score of a 1, or not, 0. So the idea is we want an algorithm that will analyze the reward or outcome to adaptively reweight randomization during data collection. And the idea here is the assignment probability, the probability of assigning you to arm A or arm B, is going to be higher for arms or explanations with a higher probability of being judged helpful. So as data is collected from any of 20, 50, 100 people, the probability of assignment to arm A is changing from 0.5 to 0.62 to 0.71 to 0.83 and so on. Does that give us a sense of what, in this context, we're thinking of as adaptive experimentation, especially with respect to like giving people better outcomes, kind of maximizing the reward, the value of what people are receiving? And so, that's the kind of classic banded setting. And so in this talk, at least I'm going to focus on Thompson sampling. So based on Bayesian inference, this multi-arm banded algorithm Thompson sampling, the assignment probability to arms is proportional to the posterior probability that each arm is optimal. So in this formulation, you have a set of actions, for example, different explanations of a concept. Then you have a reward or outcome, R. For example, if students judge the explanations helpful for their learning, it might get a score of 1 or 0, so binary reward. And then you need a policy or policy learning algorithm. And in this case, that's what Thompson sampling gives. So for example, when you have a 35% chance of being assigned to arm or explanation 1, 65% to arm or explanation 2, the idea is that that assignment probability is meant to be proportional to the posterior probability that the arm is optimal. So then you're going to need some kind of model. So in this setting, we think about a beta-Bernoulli model, where PI, the probability and explanation, is going to be judged helpful or not, follows a beta distribution with parameters alpha I and beta I. And in many of these settings, we set them simply equal to alpha and 1 and beta 1. So the beta with 1, 1 is basically uniform distribution. But there are a lot of interesting questions about how to set these priors, and in particular, how to collect data using uniform random to set the priors before you actually begin to run Thompson sampling.
Joseph, can I ask for a clarification that might be useful? When you mentioned the action space, could you give an example of what your actions are?
Yes. So thanks a lot, Sophia. So for example, if I give a student an explanation, that's a conceptual explanation of what standard deviation is, versus arm 2 could be a procedural explanation that shows them how to compute standard deviation. This might be an online education setting where my goal is to randomize you to a conceptual versus procedural explanation, and the reward or outcome is whether they say it was helpful or not, like 1 or 0. Does that help, Sophia, or you want to add anything on top of that?
No, thank you. That's what I wanted to add, just in case people were wondering what kind of actions you had in mind.
Yes. And then, PI is the probability of this explanation being judged helpful or not. And that's what's following the beta distribution. And the reward is basically a Bernoulli draw with the probability of success coming from that beta distribution. So you're going to have distributions for each of the arms. And as you get data, you're going to update these. And you will use these in Thompson sampling to sample arms in proportion to the posterior probability that any arm is optimal. It has the highest probability of success. Does that make sense?
Yes, that's very clear.
Great. So this was starting with the statistical, the machine learning kind of angle here, right? And these are very broad problems. There's less integration of work across different fields, from multi-arm banded algorithms in machine learning, where they may not focus on these statistical questions as much or be aware of the extensive literature in adaptive clinical trials, and also where they may not work as much with domain scientists, let's say in experimental psychology, who will actually be the ones to be using these methods. There's work in adaptive clinical trials, and I think a lot of you will be familiar with that. Technology companies are also doing a lot of what they call A/B testing, which is really just another term for randomized experiments. And they would be consumers of the methods we develop, whether it's algorithms or analysis techniques. And of course, different fields like statistics, biostatistics, machine learning, and so on, and then behavioral science, education, health, and psychology. And of course, even our practitioners, when instructors, we actually deploy experiments with instructors, and we build systems where they can actually run adaptive experiments using these banded algorithms. So how do we actually provide techniques they can use to analyze the data as well as interpret what's going on? And so the broad questions that motivate a lot of this research over the coming 5-10 years will be, what are the pros and cons of alternative methods? force statistical inference on data from adaptive experiments that are trying to increase reward? What are pros and cons of alternative algorithms in how they trade off reward, so that's the benefit to participants in the study, against the false positive rate, type 1 error, and the power? I'm going to use the term false positive rate throughout because I'm trying to come up with slides and presentations that will make sense to a machine learning audience as well as a statistics one. So I know it sounds a bit weird, but false positive rate is always type 1 error. You know, everyone here is familiar with power, 1 minus false negative rate, or the type 2 error rate. And I found that using this terminology really helps bridge that gap a bit with people in other disciplines. So these are broad questions we're thinking about. But just to kind of pop back a level, what's the value of making adaptive experimentation actually work in the real world? If we gave better algorithms or give people guidelines for how to analyze data from adaptive experiments, what would it help with? So this is where our lab, the Intelligent Adaptive Interventions Lab, integrates human-computer interaction, which is design technology for people, with psychology, and machine learning and statistics. And our goal here is how do we perpetually enhance and personalize the design of real-world user interfaces by applying statistical machine learning to randomized A/B experiments. So we've deployed many studies in education, like the example I gave of explanations for concepts, but we also have a large amount of research on mental and physical health. So right now we're actually deploying bandit algorithms to figure out how do we give people text messages that help them manage stress better or encourage them to exercise? How do we take a mobile app and actually apply adaptive experiments to figure out which prompts we give people to help them reflect on their emotions? And we actually deploy about 10 adaptive experiments every 4 months in education, in mobile health, and other settings. So if people are interested in looking at data from that or hearing more details, I'd be happy to present them. And we've actually built a software architecture service that anyone can use. It's called Mooklets that basically let you run adaptive experiments in real time and get that data. And as I mentioned, we use HCI psychology experiment with explanations and online lessons in a wide range of ways, text messages for mental health, but also emails to change behavior. How do we help people reduce procrastination in learning online? Get them to exercise, get them to give charitable donations. And one thing we're open to is really, we should maybe be focusing a lot more on adaptive experiments to help people with COVID safety, like behavior change of physical distancing, or even engaging in vaccination. Because the psychology of exactly what message you send someone is a great place to apply adaptive experiments because small changes in how you frame it can have a big impact on behavior. And the kind of vision here is that we want to use adaptive experimentation to perpetually improve technology. So for example, tackling a problem in HCI education or health, we want to design a randomized experiment, maybe drawing on psychology, but then we deploy it and analyze data adaptively. It can lead to enhancement or can lead to personalization, figuring out that one arm is better for a subgroup of people. But then we don't stop there. We then actually keep adding new arms over time. So in a way, like a text messaging system for mental health is going to be perpetually improving because we're going to apply adaptive experiments to figure out what's effective for who. But then we're going to keep adding arms as we get new ideas. And so I think you all can see that this has a lot of practical promise to keep improving technology. But also, it raises a lot of interesting statistical questions. How do you analyze this data? How do you use data from past trials? What happens when you add arms? And so there's a whole range of different problems that we're kind of trying to bring to the community in statistics and machine learning to be tackling. And that's the software framework that lets us do all of this. So to return to the overview, I started with an explanation of adaptive experimentation, the kind of key thing we're interested in, and how this can actually help us improve user interfaces perpetually for help behavior change in education. So the first set of results will be about trying to characterize biases in adaptive data collection using Thompson sampling, where we show empirically in a particular context how using Thompson sampling and this band algorithm can actually why it increases false positive rates and why it reduces power. Then we consider how do we tackle that by actually modifying statistical tests using properties of the algorithm. And spoke with Nina and Sophia, where we actually look at trying to get an algorithm-induced distribution of the test statistic and use that to control the false positive rate. But then that actually has a really bad effect on power. So we look at actually now, how do we modify algorithms to improve analysis? How do we have statistically considerate banded algorithms that will actually try to collect data that allows scientific inference as well as having participants? And I'll close with some ideas about future work and ongoing work. So this first line of work is under review of the Journal of Machine Learning. And I'm actually going to pause sometimes to let you all read the slides quickly, so you don't have to wonder whether you should listen to me or read it. So as I mentioned before, this is all using the algorithm Thompson sampling with a beta-Bernoulli reward model. And we're going to focus on two-arm trials for now, because if issues come up in the simplest case and we can't resolve them, they're going to be even more complex in settings that have multiple arms, in factorial designs, and in settings where we have covariates and we're trying to discover how to personalize while adapting the trial. So we compare uniform random adaptive experiments in terms of false positive rate, type 1 error, power, and also reward. And we're going to focus on, in this presentation, on two real-world environments. An arm difference of 0, for example, if the probability of success P1 and P2 are equal to 0.5, and an arm difference of 0.1. So if P1 might be 0.45, P2 0.55. And we evaluate a lot of this for the Walls z-test as how we're doing hypothesis testing, because it's really key for analysis of this data to be doing hypothesis tests. That's what most behavioral scientists are using. So we have to, even if we use approaches based on Bayesian inference like Thompson sampling, we really need to be able to do hypothesis testing. So in our setting here, which was those arm difference of 0 and 0.1, with about 785 participants, that's the number of participants you need to get 80% power to detect an arm difference of 0.1. We find that actually Thompson sampling instead of uniform random drives up the false positive rate from 5% to as much as 13%. And it reduces power from 80% with uniform random to 56%. And so this is empirically fleshing out a particular context, things that have come up in a lot of the work in adaptive clinical trials. So what is it that's driving this kind of effect? And this is some of the simulation work we did and looking at some real-world data sets to try and characterize more precisely. What you're seeing here on the vertical axis is sample estimates of the means. On the horizontal is number of participants. So going from participant 1 to participant 785. And the blue is basically sample estimate of the mean P1, orange is sample estimate of mean P2. In reality, these two means are both 0.5. But what we're showing here is what actually happens when you get a false positive and why. The problem with adaptive data collection for Thompson sampling is that sampling variability will at some point lead to a sample estimate of a mean looking lower than another, right? But what happens when that happens, as you see with the orange dots? When it looks lower, just by chance, the algorithm will actually start assigning more people to the seemingly better arm. And what that means is that you never actually get enough data to recover from your incorrect inference that the sample mean is lower. It's already 0.5, but as soon as it looks bad, you stop sampling. And so even though you have high uncertainty, the sample estimate of the mean is low. And what happens is you actually get more and more certainty in the estimate of the seemingly higher mean, which is near its true value of 0.5. But that means that you eventually will be more likely to draw a false positive, because there's evidence that there is a difference between the means, but it's driven by the fact that one mean is underestimated. Does that make sense to people in terms of illustrating why these false positives are occurring? And what you see in the green is the assignment probability. So at the beginning it's 50-50, but it very quickly goes high, and you kind of always assign people to that seemingly higher arm. To kind of illustrate here in terms of the underlying beta distributions, even just a few observations, for example, in this R1, some success, 2 success, 6 failures, will give an estimate of the proportion, success proportion that's lower. But then over time, you keep assigning more and more people to the RMB. Just giving you a sense of what the underlying distributions are that are being used to estimate the posterior probability. And what we've shown in this paper is also that it's not just the case that using a Bayesian analysis will fix this, because it's actually biased and estimates the sample mean. And so Bayesian analysis doesn't just correct this, it's actually in terms of how data is being collected. In terms of false negative, that's probably more intuitive to a lot of you, but basically, even when there's difference in means, so the blue one, P1 is 0.55, orange P2 is 0.45, the algorithm will correctly, the green is assignment probability. It'll correctly learn to put more people into arm 1. But the problem is that because you never put that many people into arm 2, you don't actually get very high certainty that there's a difference in arm means. And what's kind of interesting is the same effect that happened before happens here as well, which is you will actually be negatively biased. So even though the arm P2 might be worse, in a lot of our simulations, we show that if it's actually 0.45, there's a negative bias that might be estimated at 0.41. Because again, when random highs and lows lead the worst arm to look bad, it's often looking even worse than it truly is. So what's interesting is you actually have a negative bias where you think the worst arm is worse than it really is. Like you might think it's 0.41 instead of 0.45. Despite the fact that you've actually got a bias that increases the difference in sample estimates, you've actually got lower power because of that lower certainty. And so there's kind of two competing influences: the difference in R means, in sample estimates of R means, but also the difference in certainty. And what you're seeing here is that in the case of power, the reduced certainty in the lower estimate is outweighing the fact that it's actually a bigger bias or bigger difference in the difference in R means. So to illustrate this in terms of sampling distribution, what you see on the top is that this is the wall test statistic and the uniform random assignment. And so when there's arm difference of 0, that's the one on the left, the blue. And on the right is the arm difference of 0.1. That's the orange on the right. And so that's the kind of standard setup. We can set things to get a 5% approximately false positive rate and an 80% power, which again is chosen because for n of 785 participants, that will give you a power of 80% to detect a difference in R means of 0.1. So that's the kind of standard setup. But what happens below? What you're seeing in figure B is the wall test statistic distribution under Thompson sampling assignment. So again, the blue here, you can see that when there is no difference in R means, the distribution test statistic is pushed out. And that's actually why you get more extreme values, because again, there's a bias where you're likely to, more likely, 13% of the time is 5%, to see larger differences in sample means, because as we showed in the previous false positive example, at a certain point you stop sampling when something's looking lower. What you can also see is that actually under the arm difference of 0.1, the distribution of the test statistic is also actually reduced. And that's again because you don't get such extreme values because you're not certain in your estimate of the lower arm. So does that get people a sense of how these previous illustrations map onto actually the distribution of the test statistic under Thompson sampling versus uniform random?
I would say yes, Joseph. But I'm a co-author in the paper, so I think I'll let others say, but it's clear to me.
And I'm also asking these rhetorical questions. One thing I did in my PhD was actually write papers about how asking questions helps people learn. So I'm posing them kind of rhetorically to get people to stop and think and pay attention to important things. So here's another problem. As we mentioned, it's not that a Bayesian analysis would fix this. One of the kind of key insights we especially try to spell out for the machine learning community is that you can't necessarily trust that a high assignment probability means that there's a difference in R means. And this is really problematic because a lot of people, even reviewers up to now, will say, well, actually, if there was no difference in R means, then Thompson sampling would just assign people 50-50. But that's just not the case. So when there's no difference in R means, assignment probability in Thompson sampling is 0.8 or higher in 53% of the simulations. When there is a difference, such as arm difference of 0.1, the assignment probability is 0.8 or higher in 95% of the simulations. And that's what this table below is showing. It's basically a histogram saying, how often is the assignment probability between 0.8 and 0.9? Well, that's 20% of the time, if there's no difference in R means. How often is it between 0.9 and 1.0? 33% of the time. And so what's problematic here is that, of course, when there is a difference, the assignment probabilities are higher. But even when there's no difference, Thompson sampling will converge in a way on one arm in a way that suggests there is. So even if there's no difference, 53% of the time, the assignment probability at the end of the trial will actually be 0.8 or higher. So hopefully that makes clear to everyone how the behavior of the algorithm, the fact is putting more people in one condition, the fact the posterior probability of an arm being optimal is higher, does not in itself provide that strong evidence as you would have liked for there being a difference in R means. So what are the key takeaways from this part of the talk? So we try to characterize this bias in terms of increased false positive rates and reduced power, and why they occur in terms of random highs and random lows, and also why the assignment probability, that posterior probability in Thompson sampling, can actually be misleading. So this then takes us to the next part, which is, well, how do we address this? How can we help behavioral scientists actually know how to analyze data, or at least put some bounds or some understanding of how certain or not they can be about the inferences they draw? And so one broad approach, which we're just giving one simple example of, is to modify statistical tests using properties of the algorithm, like Thompson sampling. So the problem is the Thompson sampling changes the distribution of the wall test statistic relative to uniform random. So a potential solution could be to adjust the standard wall test to account for the adaptive nature of data collection. And we call this the algorithm-induced test statistic, and it's based on approaches raised by Smith and Villar and others. So the key idea is actually kind of simple in this sense. If you look at actually this figure below, right? Let's look at this image. This is the same thing reproduced from before of the Thompson sampling induced distribution of the wall test statistic. But what you can see is we could adjust the critical values. Instead of being 1.96, we can change them to 2.6, and that will provide a controlled 5% false positive rate. So what you can see there is, actually, I'm not sure if you all can see my cursor. Sorry, I should have checked that actually. Okay. Let's see if that laser pointer is showing up. Okay, I think you can see the laser pointer now, right?
Yeah.
Great. I should have done that earlier. Thanks. So this is the 1.96 cutoff, and that's what gives a 13% false positive rate. But we can adjust this by actually a simulation-based approach where we actually simulate under the null. So that has issues because we have to assume that we know what the null is or fit it from the actual data in a trial. So we simulate on the null at P1 equal to P2 equal to 0.5. And then we actually set the cutoff to be 2.6 based on that. So we get our controlled false positive rate of 5%. So that's nice, that's good. Now, of course, the challenge is that now our power is much lower. Our power is actually 17%, which is really incredibly low. So I think this is useful because it illustrates one kind of approach we can take. Incorporating properties of the algorithm by actually simulating, assuming we're collecting under the null data using Thompson sampling, and then adjusting our critical values. We also looked at a bunch of other approaches in the paper, such as inverse probability weighting, with the idea being that we want to actually eliminate bias in estimates the sample means. And so that has some benefits. It doesn't completely control the false positive rate. It reduces the power a lot. And we can talk more about that later. But what I hope was taken away from it was just one illustration of how we're trying to tackle this problem and our first steps towards it. And we definitely welcome other ideas. This will be really key to getting behavioral scientists to adopt it. But I think it also points to the need to tackle this from both sides, or at least in tandem. How do we actually modify algorithms to improve analysis of data? How do we design algorithms that are more statistically considerate? Because they're not just trying to maximize reward, but you also want to enable better statistical analysis, lower false positive rate, and higher power. So here's just one example of a first step towards an algorithm that does this. And this is by taking a hybrid Thompson sampling and uniform random approach. And this slide is borrowed from Nina. Thank you, Nina. So here's the idea. Let's tune Thompson sampling to increase uniform random assignment when they're non-existent or small effects. Why does that make sense? Because then there's a minimal loss in terms of reward. If there's no difference or small difference, we don't really care so much about giving people better arms. So let's do more uniform random assignments so we can actually get greater certainty about what the true effects are. On the other hand, when there are large effects and substantial reward to be gained, do less uniform random and more Thompson sampling assignment. So what you want is an algorithm that will actually cleverly choose between some proportion of the time giving uniform random and some proportion of the time giving Thompson sampling. And so the idea here is of the algorithm we propose, and it's under review now, is Thompson sampling posterior probability of difference, or TS positive. With probability phi of t, t is participant 1, participant 20, participant 100. Probability phi of t, choose actions uniform random. With probability 1 minus phi of t, choose actions with Thompson sampling. So now, of course, the question is, what is that probability phi of t? And in the paper, we actually look at what happens when you fix that probability. You just fix the 10% or 20% over the full trial. We look at what happens if you just decline it as you get more data. But in this algorithm, we try to do something that's data adaptive. So we set phi of t, the probability uniform random, to be the posterior probability at time t that the difference in the expected mean outcomes is less than some threshold c. And we can actually compute this with posterior sampling, just like Thompson sampling. So just to say that again, did that clear to people? The phi of t, the probability of doing uniform random, is the posterior probability that the difference in R means is less than some threshold c. For example, it might be the probability that the difference in R means is less than 0.1. If that probability is 30%, then you do 30% uniform random, and 70% of the time you do Thompson sampling. If the probability of the difference in R means is less than 0.1 is 5%, then you're only doing 5% uniform random. 95% of the time you're doing Thompson sampling. So is it clear to people how this approach actually allows us to specify how much we care about an effect of a certain size, and kind of say that, well, if the effect is smaller than this size, then we should be doing uniform random in proportion to that. If the effect is bigger than that, we want to do more Thompson sampling. Does that make sense to people? Any questions on that?
You are going to tell us how to choose C in a moment, aren't you?
Gosh, you'll have to make my life hard, right? I will talk about how to choose C. I'm happy to talk about it, but I think that's something that we're still trying to think through and figure out. We have a bunch of data in the papers on it. But yes, I'd be happy to discuss that actually. It's not in these slides, but I'm happy to discuss it more.
Thank you.
Yeah, but thank you for raising that. I thought I'd have a lot less time. Hopefully that doesn't mean I talk too fast, but anyway. So everyone's kind of clear now on how this algorithm works, right? In terms of mixing uniform random and Thompson sampling. As the probability of uniform random is the posterior probability, the difference in means is less than some threshold. So how does this perform? I'll skip over this, but basically this is how, if you see a machine learning paper, people tend to write out the algorithms, right? For every observation, for each arm, you sample, and then based on the posterior probability difference in R means being less than C, you do uniform random. Otherwise, you're going to use Thompson sampling. And then, of course, you update your posterior based on the reward you observed for a particular arm. Okay, so there's a lot of data in here, but what we're breaking up is uniform random, Thompson sampling, Thompson sampling positive with C of 0.1, and false positive rate and type 1 error, the proportion of participants in the superior arm, which of course for arm difference is in quotations because there's no superior arm. It's just how often more people are put into one arm that seems superior, and the reward. So let's look first at false positive rate. So in this setting, uniform random would give us 5.5%, false positive rate, type 1 error. Thompson sampling is 13.5. But what's nice is that Thompson sampling, when you choose a C of 0.1, if you use Thompson sampling posterior difference, actually the false positive rate is lower. It's 7.8. And why is that? It's because when there's not much difference in R means, it does more uniform random assignment. And that's good because that actually allows us to have a lower false positive rate because we get better estimates in the certainty of each R mean. and we put more people into each condition. You can see that by looking here. The proportion of people end up in an arm that seems superior, but isn't really. Uniform random is 50%. But remember, Thompson sampling, even if there's no difference in arm means, puts a lot of people into one arm that seems superior. Whereas Thompson sampling puts you a difference. Because it's actually got that uniform random component, the response to the fact that there's not much evidence, there's a lot of evidence that the arm difference is less than C of 0.1. We'll put more people into uniform random. So is it clear now how, when there's no difference in R means, Thompson sampling positive is actually doing a better job on false positive rate because it's putting more people into conditions equally by assigning more uniform random, as there's not much evidence for a difference in R means. Well, what about when there is a difference in R means of 0.1? Again, uniform random has a power that we designed this study for. 785 observations will give us power of 80% or thereabouts. Thompson sampling typically reduces that to 56% because you're doing uneven assignment, and so you have less certainty in the estimate of the lower arm. But Thompson sampling positive actually gives us pretty good power, 77.5. So we're actually getting a much better power. And why is that? Again, because uniform random is putting 50% of people in the actually better arm. Thompson sampling is putting 86% over the trial of 785 people. And Thompson sampling positive is doing something a bit in between. It's not putting as many people as Thompson sampling, but it is putting more than uniform random. And again, you want to contrast 73% of people being in the superior arm with 55% when there's no difference in R means. The key thing is that it's more adaptive to whether there's a difference or not. To decide the difference.
So can I ask a question?
Yeah.
So this hybrid scheme, so at time t, when the estimated difference is less than C, you revert to uniform random sampling. So in your table here, what proportion of time steps are you random sampling versus Thompson sampling?
Yeah, that's a great question. I think that's a plot that I should actually include, right? Let me think for a second if I can reconstruct it mentally. So I would say that just to be precise, I'm not sure if what you said is exactly how I would say it. It's not that you explicitly revert from a Thompson sampling a uniform random phase. In your 785 participants, every participant you choose whether to do uniform random or Thompson sampling. So as time goes on, you're always mixing uniform random and Thompson sampling. The thing is that probability of uniform random is the posterior probability that the arm difference is less than C of 0.1. And so that probability might start off, for example, at 20, 30%. Then it might actually decrease over time, or it might increase over time. I'd have to actually go and pull the simulations for you to show that. But maybe actually, what I can do is I can actually pull up the paper and show you some of those results in a little bit.
That would be great. Thank you.
Yeah. I can look for it now, but yeah, let me pull it up just in a second. But that's a nice thing. I think the results we will get at that, but that might be a nice table for us to actually plot to illustrate this more clearly and how it's behaving, right? And if you look at reward, again, uniform random 50 reward basically is assigning people. Remember, you could get 0.55 if you put everyone in the better arm, 0.45 is the lower arm. Thompson sampling gets you 53.6 in this trial of 785 people. And Thompson sampling posterior difference gets you 52.4. So again, it's a nice intermediate interpolation between these. So getting towards that question of how you choose C, right? This is something that we really have to think about a lot, and I think is like a good bunch of follow-up research on this topic. Let me not answer that question directly, but let me ask you a question. One might say that, if you choose C as the actual arm difference, if it's 0.1, you want to choose C at 0.1, maybe that's a reasonable heuristic. But what if you actually choose C slightly bigger? So suppose C is 0.2 and the true arm difference is 0.1. Well, what that says is, what's the posterior probability that the arm difference is less than 0.2? Well, actually, it's going to be not that high, right? Because the arm difference is 0.1. Sorry, it's going to be high because the arm difference is 0.1. So you'll actually do a lot more uniform random. So what happens here is that you actually end up with a false positive around 5.4. You end up with people being put pretty close to uniform random, and so your power is high. Again, because the proportion of people in the superior arm is not very different. So you know, also you don't get much reward. So the idea is that if your C is chosen, so it's higher than the true arm difference, then that means you'll do more uniform random and get less reward. And maybe that's actually good. Maybe, for example, you choose a C of 0.2 because that arm difference is actually important. If it's less than that, then you're more willing to have scientific knowledge about what's going on, and you're less concerned about the harm to participants. And of course, you can think intuitively, if you choose C as less, for example, if you choose C as 0.05 as opposed to 0.1, then you're going to do a lot more Thompson sampling. So if you choose C to be smaller than the true arm difference, then that's where you're going to get a lot more reward maximization. So what do you all take away from this so far? So I think this is just one first step towards a general kind of approach. How do we have algorithms that explicitly combine uniform random and Thompson sampling? And we raised one approach, right? Estimate the posterior probability of difference in R means is less than some value C, and then do more uniform randomization with that probability. And the idea being that it kind of allows you to interpolate between those approaches to get a balance of false positive rate and power and reward. But I think that the key, and you see how it does that by putting more people in uniform random when differences are smaller and existent, more people in Thompson sampling, and the better arm when they're bigger. And I think the key thing here is being data adaptive. We don't know which world we're in. We don't know if the arm difference is 0 or 0.1 or bigger. So how do we design algorithms that are actually going to be sensitive to that? But really, this is raising more questions than it's answering. How to set C? Are there other ways to do this? Are there better ways to do this? So just to review the talk, we started with adaptive experimentation. That's a key topic we're thinking about, especially adaptive experiments that focus on helping future participants by maximizing reward and using data to get better arms more quickly. I outlined how this is what our lab focused on because this is how we can improve user interfaces for health behavior change in education, because we can keep doing experiments perpetually, keep adding new arms, whether it's text messaging for mental health, getting people to exercise, or online lessons. The first part of the talk, based on that under-reviewed Journal of Machine Learning paper, tried to characterize some of the biases in adaptive data collection, giving some empirical context to past findings theoretically and empirically in adaptive clinical trials in machine learning and statistics, where we illustrated that an algorithm like Thompson sampling will increase false positive rate because when they're random lows and highs, you kind of stop sampling one arm and you never really get more data to unlearn and realize that the arm's not as bad as you think it is. But you put more participants in the arm that seems better, and you get more and more confident in that true correct estimate. And that leads to false positive when you have high certainty in a true arm, but low certainty in an incorrect underestimated arm. We also illustrated the reduce in power, again, because you have less certainty in the arm that is in fact lower. And we showed how when Thompson sampling assigns people where the assignment probability is the posterior probability that an arm is optimal, you actually can't trust that probability nearly as much as you think you could, because that assignment probability, the posterior probability that an arm seems to be optimal when it's exactly the same as another arm, can be 80 or 0.8 or higher in 53% of simulations. We illustrated just one first step towards how do we kind of tackle these problems, these biases, in terms of modifying statistical tests using properties of the algorithm. And the first result was that algorithm-induced test statistic. So under the null, trying to use simulations to assume the data was collected with Thompson sampling, get a distribution of the test statistic, and adjust the critical values from 1.96 to 2.6. And that did let us control false positive rates, type 1 error to 5%, but power was really low at 17%. And we also looked at some approaches like inverse probability weighting, which we can talk about more, which got it to about false positive rate of 11% versus power of 35%. But the kind of key insight here is this is the first step, and we're very interested in other approaches like these. and especially approaches that we can get an experimental psychologist, a clinician, to actually use in their deployments. We also looked at now, given how we've characterized the bias, it seems that actually we might need algorithms to be more statistically considerate. How do we modify algorithms to improve the analysis? And that's what we just talked about. One idea being to combine uniform random and Thompson sampling by saying, let's draw uniform random with the posterior probability that the difference in R means is less than some value, C. And the intuition being that when there's not a big difference in R means, we should do more uniform random and get better certainty and false positive rate and power. When there is a big difference, we should do more reward maximization and Thompson sampling. But again, figuring out what small and big means is a tough question. So in terms of future work, I think I should have had exactly what people said there. How do we choose C? How do we give guidance to people choosing C? How might we learn C or adjust it using an algorithm so you can adjust C based on the data itself? In general, what we want to do is make these more applicable in practice. So a key ongoing work is better theoretical analysis of this algorithm. Understanding and mathematically characterizing how its behavior depends on different features of the arm differences, the sample size, different ways we can actually set up the algorithm and apply it. Another thing is to generalize it to actually having 3 or 4 or more arms or factorial designs. One thing that has actually received surprising little attention is how many participants should we do uniform random burn-in before Thompson sampling? In our case, we actually start Thompson sampling from trial 1. But it would make sense to actually have a period. Is it 50 participants, 100, 200? What does it depend on? Where we might actually not want to do any reward maximization until we have a better estimate. And maybe that would actually reduce the bias. So we'd want to characterize that, but then also think of which algorithms could be used to actually set that period of burn-in based on the data itself, which again introduces all kinds of other issues. Another issue is varying batch size for how often we update the posterior. In our simulations, we've been using a batch size of 1. After every observation, we update it. But that raises a lot of issues when you have non-stationary data. And it makes it hard to really analyze the data as many batches and understand what's going on. We'd like to tie this work more closely with the relevant literature on optimal experimental design. I think that comes out of engineering more and some areas of statistics, where the goal there is not necessarily to optimize reward, but if we could more explicitly formulate what we're trying to optimize with reward along with properties of an estimator, that might be a better framework. And that ties in actually to how can we begin to better characterize what's the objective function that combines reward, false positive rate, and power. For machine learning people, they'd be a lot more able and willing to help us kind of develop algorithms if we could say, well, what are we trying to optimize? How much reward for how much false positive rate and how much power? Now, the complication here, though, is that often behavioral scientists may not be able to articulate exactly what that objective function is. And so it's a bit of a chicken and egg problem, where in a way we have to give them some simulations and some work to show, here's where you get the biggest bang for your buck. And that's something I can actually show you in Thompson sampling posterior difference, how we began to look at that. But I'd be super interested to understand people's ideas about other approaches we can take or considerations we should have in mind. All right, thank you so much.
Thank you, Joseph. Brilliantly explained. Yeah, really enjoyed it. I will give time to people think of questions. I think you might also see if you want to expand on Simon's question around if you wanted to get the paper. But I should say, meanwhile, that you should probably take all the credit for the term statistically considered band-aids. I think I haven't heard that from anyone else. I'm not sure if it's yours or not, but I think that's a very good description of a lot of the work that's coming out of making inference after having used all of these algorithms and being robust. So it's a very nice term.
Okay.
Any questions from the audience? I think Simon.
So, sorry, this is a distinct question to my earlier question. I was wondering if you had any view to the types of settings. So in this reward question, the 2 arms are you viewing them in a sense where the 2 arms aren't necessarily one is better than the other, but one might be better for a type of person, or are you viewing it as a population type question? Because at the start of your talk, you indicated you might be trying to tailor the arm to the person, but that's a different reward to say to pick in the best arm at a population level. And I'm not clear where that's coming through at the end.
Yeah, no, and that's a great question. We're actually interested in both of them. And that's like the contextual banded setting where the reward function depends on the arm and also a function of context, like someone's level of knowledge, whether someone's been engaged with your text messaging service or not. So we're definitely interested in both of them. I actually started first with the contextual bandits and then realized that actually even just tackling it for the bandit two-arm case was sufficiently complex. We should tackle that as well. But we're actually doing both of them. So in our mental health deployments, for example, now we are deploying contextual bandit algorithms where we have variables like, has someone engaged with the text messaging service in the last 3 days or not? Is it a weekday or weekend? And we're trying to actually figure out which of those arms is best given those features. So we're definitely interested in that. It's just that I didn't present any work on it.
Nina? Unless, Joseph, you want to use the paper for answering the question that Simon posed during the seminar.
Yeah, and these papers are kind of under review, so just keep in mind, or at least, if you're going to work on it, let us know. But I think this question about how to choose C, I think it's a great one, right? And I'm not sure if we have great answers for that, if it's just because we're just doing this work now, or if it's just already thorny problem that's harder than we realize. But to give you an illustration of one thing I think would help a behavioral scientist from trying to talk to them. What you're seeing here is the false positive rate and how it changes for C. So C is going from 0 to 0.2, and the true arm difference is 0.1. Then we're showing how power changes for C and reward changes. So what you kind of see here is that basically, as C comes down, if the true effect is 0.1, that's pretty good. If you go a bit beyond 0.1, like, to 0.12, you actually get a false positive rate down nicely to like 6%. For power, though, you kind of start to get diminishing returns here. When you go to C of 0.1, you get a power of 77%. If you go a bit more, you get to 78. But before, you actually got you got a lot of returns and then it dropped off. Whereas for reward, it kind of just like, here's where it starts. It's pretty linear. So I know this is a lot to absorb, but I think the key idea here is that I think what would help behavioral scientists sometimes is to be able to say, well, as you choose C, here's how much bang you get for your buck. When you shake C beyond the true arm difference, then you keep your false positive rate going down for a bit, but then you get diminishing returns. For power, as soon as you hit it 0.1, you're kind of going to get diminishing returns right away. For reward, you can keep going all the way. So I think that this kind of analysis can maybe help people understand how to choose C. And right now we're just at heuristics. How do we tell a behavioral scientist or an instructor or a clinician what is a big effect size that they care about? That's kind of hard to know, right? But again, a heuristic here being try to set it to approximately what you think is a small or big difference. I think it would be really nice for us to think of how we could actually help someone specify what they think a small or big difference is, and then actually adjust C based on the data that we see in the first 50, 100, 200 participants. That could be another idea.
Nina, do you want to pose your question?
Yes, thank you. So thanks, Joseph, for the very clear exposition. It was very nice. And so my question is related to some insights related to how the standard statistical testing approaches perform in these adaptive settings, in adaptive randomization settings. And more specifically, it's related to the relationship between bias and frequentist properties such as type 1 error and power. So from the plots that you shown here, it seems that one of the problems which may guide type 1 error inflation is basically that one arm is underestimated, so it's affected by a sort of negative bias.
Yeah.
Right. So can we say that actually correcting that bias, we will have an improvement in terms of frequentist properties, or is there any other aspect which actually drives type 1 error and power, and not only bias as the only driver?
That's it. So to echo back the question, is it really bias you have to focus on and reducing bias to get better frequentist properties? Or are there other things that are driving the false positive rates that we should focus on?
Right.
That's a great question, Nina. I think I have to think about that more because nothing is popping to my mind right now in terms of that. I mean, yeah, nothing's quite popping to my mind right now. I think maybe one thing that I think is always a problem, and I want to get to David's question, is the whole. We do frequent disanalysis of data from experiments. That's just how the world works in terms of publishing and analysis, and it's well understood. But one thing that I think comes up here, we don't know which world we're in. If we knew that the effect was going to be 0 or small versus if it was going to be big, we'd have a much better idea of what algorithm to apply, right? Mm-hmm. So one thing I could imagine is maybe we could actually mitigate some of the issues with bias if we had some like prior estimates of how likely it is for the R means to be non-existent or 0. How likely is this for the R means to be 0.1 or 0.2? And I know this is actually kind of an unusual question, but I bet there's some statistics literature on this. But if you actually have some prior belief about the magnitude of the effect, could we incorporate that into the algorithm we're using? And then maybe that would actually be a way to worry less about bias. Because, for example,
So, for example, I've seen that in the slides you mentioned IPW at one point, right?
Yeah.
With the IPW, was it able to correct the bias and at the same time adjusting?
I think the point that Nina is trying to make is that if with IPW you might get rid of the bias in the estimate, but you still have a distributional problem for errors, and that's what we saw. Can I quickly pass to David so that we manage to get one more question in, and before we have to close up? David.
Oh, thanks. Thanks for a really good talk, Joseph. I guess I had a slightly more general question in terms of what your thoughts were if we move from a 2-arm setting to a multi-arm setting. Would you expect some of these issues to get worse or better? Or just wonder what your thoughts are.
Yeah, no, I think that's super interesting. I think that's where we might actually get more power, right? If we want to figure out like power to detect the best effect relative to the second best, that could be an interesting kind of direction. And so I imagine in that setting we might actually get better power and more reward even by applying a banded approach. Where would we actually expect like things to get worse? That's an interesting question as well. I mean, maybe the bias issues that people are emphasizing, like Nina and others, might be compounded because now we have multiple arms that we're trying to keep track of, and there's more room for things to kind of go off the rails. And maybe that's where something like inverse probability weighting might be more useful or less useful. Because like Sophia and Nina said, it does help correct the bias, but we're trying to honestly characterize it properly and understand why it's happening, but it does still drive a false positive rate, possibly because there's more variance in the estimate of the mean. And so trying to understand how all that's working is complex, Maybe just to throw out one idea, as we move to the more complex case, right, like the multi-arm case, factorial designs, what would be nice is if we had like posterior properties we could trust, right? Because if we have those, then we've got the correct thing, and that's what statisticians could help us with that. If we have those, then we can hand those to someone and they can optimize how they like. They can say, I care this much about reward, this much about power. But honestly, that's a hard problem like to tackle. Like Nina and I have talked a bit about that a while ago.
Okay, thanks.
Thank you. So I think we're on time, so we probably have to wrap up. Thank you, Joseph, again for agreeing to giving the seminar. It was a real pleasure. And anyone else that may have any questions or comments, feel free to reach out to Joseph. He's always very welcoming and he's always very excited to share his experience and his interest for this topic. So please do reach out. Anyway, thank you, everyone. And thank you, Joseph, again.
Yeah, no, thanks, everyone. Yeah, email, give suggestions, tips, anything else is welcome.
Okay. Bye, everyone.
See you.